Now, this is typically the average velocity. This means velocity average in physics books. Okay. Now, that is, of course, defined by delta x over delta t. Meaning, if we have t2 minus t1 in the denominator and the numerator, I have this. You get it? X2 minus x1. And I'm using this x as a function notation. Have you seen this before? Instead of f of, yeah. So this is very typical in college texts, and especially in physics, but in math as well. Okay, so shall we calculate it using this? And if we calculate it, and as you can see here, this point here is 2, and this point here is 3. So we are supposed to calculate this between 2 and 3 seconds. Okay. So this side, it comes over, and this becomes f of 2 squared. And this thingy now becomes 3 squared. So far, so good? Okay. Now, then, so denominator becomes 3 minus 2, and the numerator is 3 squared minus 2 squared. Eh? Somebody punch the calculator and tell me what this thing becomes. Oh, come on.
5.
This is calculus. 5. Right, you need a calculator for this, right? Okay, that's 5 meters per second. So this is an average velocity between 2 and 3 seconds. Because your velocity changes, you're speeding up. You're clearly accelerating. Can you tell if it's accelerating by looking at the graph? If you're a physics student, you better, even if you're not, still, right? Wait, somebody got kicked out? Okay, let me admit it in. Now, so this is great if you're planning a road trip or something. See, I went to Las Vegas and Grand Canyon over during summer. Do you guys know how far Las Vegas is from here? It's about 300 miles. And it took us 4 hours to get there. My normal, light traffic, my normal driving the speed. What is my average velocity? Oh, come on, 300 divided by 4 is not that hard. 3 over 4 is 75%, you get it? So 75 miles per hour. That's nice and swell if you're planning a road trip, but in case I was doing 90 and got pulled over, which I did not, but if I did, then if I gave an argument, but officer, my average velocity is way under the speed limit, so you should let me go. And that doesn't fly, right? So something about that average velocity, it has its moments, it's great, but sometimes it's very useless. So when we say velocity or speed, whatever your speedometer, whatever that radar gun of the CHP says, that is your instantaneous velocity at that time, right? So now instead of finding an average velocity between 2 and 3 seconds, we want to know what the instantaneous velocity is exactly at 2 seconds. Okay, so we need the definition. Here's the definition of instantaneous velocity. When we write V, it means instantaneous velocity without any notation. Okay, that is same thing, delta x over delta t, except we take a limit as delta t approaching 0. Okay, that is the definition of instantaneous velocity. Now we can estimate it by using delta t to be 0.01. I have graphics for you on what that means, so let me show you what that means. So I have my, say this is 2 here, and this is the other point, and I want to make this thing, it used to be 2 to 3. There, you know what I'm saying? And then I have the computer measure the slope, so it's 5, approximately 5. But if I make this thing 0.01, then it comes all the way here, and then 2.01, about almost, so close. I got too close. I mean, something like that. You know what I'm saying? So can we do that? Yeah, sure. So we can say velocity at 2 is equal to, now on the denominator, so what I want to do is go a little bit here. Let's exaggerate, and this is 2.01. You know what I'm saying? And this is 2.01 squared. So we have 2.01 minus 2, and then you have 2. I'm going to write it as with a one notice frozen. It doesn't want to erase. Oh, now it erases everything. Isn't that nice? So I'm going to have this 2.01 minus, how about that? You get it? Okay. So do we have to work this out? This is 2.01 squared minus 2 squared over, this is 0.01. Somebody punch the calculator and tell me what this is. And some of you can still do it without a calculator too, but okay, feel free to use a calculator. What is it?
Is it 4.01?
4.01, okay. Great, now, right? You guys agree? Let's see how many points you will potentially lose if you did such a thing. Say, let's grade this thing together. There are two problems with it. Can somebody figure out what those two are?
Units, maybe?
Oh yeah, units, huh? Whenever you write a number down and don't have units, you should feel weird. You know what I'm saying? I mean, that number looks very naked and uncomfortable. Like you have to that's like, you have to have an uneasiness. Okay, some people being really, really anal in math, if there are no units, then they write unit as a unit. I mean, okay, I'm not really that anal. Okay, so here's a rule of thumb. If there are no units ever being mentioned in the problem itself, then you don't have to give units. However, as you can see right there, second right there, you know what I'm saying? You see meters right there. So it's like there are plenty of indicators that I want units. So that's -1 if you don't give me units. You get it? Okay, that's one deep, huge thing. Okay, what's the other one?
You're working horizontally.
Oh, that's fine. I mean, that can go this way, right? But that's fine. To me, I take it, and then like space may not be enough, so it's like horizontal, vertical. It means the same thing as long as you link it with the equal sign. That means the same thing as what I just wrote here. Okay, so that's fine.
Final statement, maybe?
Nope. Oh, okay. I'll just this. This and this, these are two different things. And you cannot interchange them. And if you don't know which one to use, I'm going to remind you by taking off 1 point each until you get it right. What are we saying here? It says estimate. Do you see that word estimate? It means this expression is approximately equal to this expression. It's not exact. It's not exact that instant. You know what I'm saying? So we have to use approximately equal to. Well then, here's another one. Well, do we use approximately equal to right there? What do you say? That's another thing that gets students all the time. Is this straight equal to, or is it squiggly equal to? I call this thing squiggly equal to. On this, you're punching a calculator, right? But in this side, it depends. If the calculator gives you some repeating decimal or non-repeating decimal, such as pi and square root irrational numbers for that matter, and if you have to round it, then it's squiggly equal to, because you still approximated this expression to be approximately equal to that. However, if this time your calculator gave you 4.01 and that's it, no zeros, right? That means it's the exact number. That means this is exactly equal to, so we use exact equal to here. Do you know which is which, the difference between the two? Okay. Now, if you have to round this thing, and use approximately equal to, then how many decimal digits is required in this class? Take a guess.
6.
Oh, how did you know?
My friend told me.
Yes, it's not 2, it's not 3, it's 6. You still have to round it, so you look at the 7th digit, and I don't have to teach you how to round, correct, right? You round 7th digit into 6, and your 6th digit has to be same as mine, otherwise I will consider it as an incorrect answer. It's a calculator, it's not you doing it, right? Writing 3 more digits it's not that much effort, that much hardship, so do it, okay? So your answer has to be correct, exactly same as mine, up to 6 decimal digits. That's my requirement. Okay, I'm kind of picky in that way. See, science background, I care about these things a lot. You know, the precision of your data. And then I will let your science teacher worry about the significant digits, okay? Even if you have to present significant digits, and all of you should know what that sig fig means, right? Say there are only 3 sig figs in this case, then you calculate all the way to 6, and then you round it accordingly at the end. Instead of keep rounding it, those are known as a rounding error, and that's a big problem. I mean, if you take any computer science classes or applied math, that's a big problem, rounding error. So your calculator will carry 14 digits altogether. You have to carry all of them, storing it and saving it on your screen, and work it through and round the 7th digit into 6. And in your science class, you round according to your sig fig. So far, so good? Okay. So that's nice and swell, except let's just look at what if, who says that we only need to go that way? Can we use 1.99? In other words, delta t, adding 0.01 to the left-hand side instead of going the other way? I mean, we could totally do this, right? Graphically, this is what it means. So we went, this is 2, and then we went that way. But instead of going that way, what happens if we go this way? That's perfectly good way of approximating that thing, and it's, you approach it close. You know what I'm saying? So let's do that. So velocity at 2 is now approximately equal to x at 2 minus x at 1.99 over 2 minus 1.99. Okay, somebody punch the calculator. What is this?
3.99.
3.99 is correct. Huh. And then, of course, one begs the question, which one is more accurate? Which one do you like better? I know the first one is easier, right? But easier does not mean right, necessarily. So which one is it?
None of them.
None of them. Oh, okay. None of them are exact. That's if that's what you mean. But which one is better was the question. It's a trick question. It's the average of the two. You take average, and then you get 4. I know, huh? Tricky, right? That's a lot of work, right? However, we don't have to do all that work. Here's a way to achieve exactly the same thing, and this is it. So this is black version, because black inks matter totally as well, right? So we go 2.01 this way and 1.99 that way. You go both ways. You get it? Okay, if you do that, somebody punch the calculator. And this is 0.02 now, right? Oh, I'm gonna change this to 0.01 in order to make it look pretty. And y'all have 4 exactly. See, that's so much better. And then you think your real instantaneous slope is 4. And we have a computer that does this. Let's see if I can make it be on top of, I guess this is as close as it will get, right? Now this, you can mathematically verify this is the same thing as taking average of the two. It's pretty easy proof. But here's the point, why this is 95% of the time most accurate approximation, and I'm going to exaggerate this to prove a point. We are trying to estimate the slope of a curve right there at that point. And if you go both ways, chances are this part, this slope of this line, will be somewhat parallel to this point. You get it? That's why this tends to be the most accurate answer. So AP accepts all three of the above. However, me, your picky teacher, I want this third way and third way alone. And then you're thinking, oh, can we just take a derivative and just get, many times you don't even know what the function is. They just give you a data table and make you do this all the time. So you have to know how to do this. Okay, and we'll take this third way alone. Okay, because the other two, if you're gonna do the other two, you have to do twice and take an average. Okay, now, but then, notice that I said the slope of a curve, right? There's, of course, the anal mathematicians will have issues with that statement, right? Does a curve have a slope? Or does it have to be the, instead of slope of a curve, does it have to be the slope of a tangent to the curve? Kind of like this. So this is the picture, right? It's a tangent. So it's really tangent and we are finding the slope of this line because curve does not have a slope. What do you say? Do curves have a slope or not? You have to pick one. You have to pick a side. There's no such thing as neutral. Either you are either for me or against me. Let me modify what Jesus said. And I go even deeper. Either you're for me. If you're not for me, then you're against me. Which way is it? No, such a narrow extreme view now, right? Anal mathematicians will say, no, some of them at least will say curves don't have slope, right? You cannot talk about, right? However, let's just talk like engineers and scientists. We live on a hill, right? Right? And I mean, it's never flat, right? So we have a slope. These hills have a slope, right? But is this surface ever straight? Totally flat? Oh, see, curves have slope. How about that? It doesn't matter. Look here, if you zoom in close enough, this curve, if you're so tiny compared to this curvature, it'll look flat to you. Do you believe it? Okay, those of you who don't, go to the other side where the other high school is, or the lighthouse might be the perfect location, or the Starbucks somewhere there, near the cliff, and look at Pacific Ocean, horizon. Does it look flat to you? Yeah, it does, totally. But you know the Earth ain't flat, unless of course you believe in the flat Earth theory. But that's not even. Even if you believe that, that's not a square. It's a disk. That's explained. Okay. Earth is not flat, but it looks flat to you because you zoomed in. You're so much tinier compared to the size of that curve. You get it? So it doesn't matter. Slope of a curve, slope to the tangent of to the curve, it means the same thing. So we just say slope of the curve. It's easier to say, right? One more thing. If you're very observant, how many of you, by showing hand, have observed the curvature of the Earth with the naked eye? PV is such a perfect, yeah, good for you. PV is such a perfect place because in a higher elevation, gets exaggerated and a little bit easier to see. If you look at the Pacific Ocean closely enough, in the middle, the horizon is so much higher than the end. It gets quite a bit lower. You can see the curvature of the Earth with naked eyes. You might want to go check it out today. I mean, it's quite a spectacular. If you add sunset to it, it's a spectacular view. You know where does Crenshaw Boulevard end? And there's a church. There's a little hiking trail in the back. Go there, and there's the highest point in PV. And like if you observe the sunset from there, oh my God, you know, bring your phones to take pictures. It's quite a view. And you can observe the curvature of the Earth. So this is like scientific expose at the same time. Okay, having said that, so now, well, that's nice and swell, but that's still an approximation, and we want it to be exact. So if we use smaller delta t, that's a better and better approximation, isn't it? Do you see it's begging for a limit? Yeah, let's take a limit. And while we are taking a limit, then there's of course the right limit. We will let it approach from this side, or we can let it approach from this side, the left limit. But graphically, at least you see it gives you exactly the same slope. You know what I'm saying? So we'll just do it from the right-hand side. It's easier to think that way, okay? So now let's go down and we'll do this exactly. I have prepared a copy of this thing, which I cannot find at the moment, so I'm gonna make another copy. So go back here. I'm gonna exaggerate this a little bit since we are taking a limit. It doesn't matter. And let me take these things apart. Then I'm going to make a copy of this picture. Okay, now, and let's put it. Whenever I make a copy like that, it always turns out to be quite big. Okay, now, so this is 2. And then let's say this thingy. So this is delta t and this is delta x now, isn't it? So we can say this is 2 plus delta t. And then value of your function going this way, this is f of 2. And this way right here is f of 2 plus delta t. You, pardon me, I jumped the gun. I want to do, that's actually my next example. I'm going to say this is easier to understand this way, so let me do this one first. This is t, and then this is f of t. That's still delta x. So far so good? Now we are still taking same delta x over delta t, but we'll take a limit as delta t approaching 0. How's that? Okay, this is my approximation of, oops, push that to the side a little bit. This is my approximation of velocity at 2. But we can use exacts equal to now because when we say limit, it's not, it means it's not equal to that anyway, right? So it's infinitely close to. Okay, now let's do this. So we have limit of, now, denominator is now t minus 2, correct? And the numerator is this minus this. So we have f of t minus f of 2. With me? Okay. And then we plug in the function. What was our function? Our x, also known as f of t, is t squared in our case, wasn't it? So, one more thing. As delta t approaches 0, I should have t approaching 2, because delta t is this minus this. It's the gap between these two numbers now, isn't it? All with me? Okay, so t approaching 2, and then we have t squared minus 2 squared over t minus 2. Wow, we have seen this before. It factors and cancels, right? So t approaching 2, it simplifies to this. And then, of course, t becomes 2, so we have 4. Exactly same thing we got it from the computer, eh? How about that? Okay, this is not exactly what Isaac Newton did. Okay, this is done in later mathematicians prefer this way more. So this is known as the alternative definition of, let's throw that term because you know what it means, derivative, you get it? So, well then, what is the traditional definition? According to Sir Isaac, you do this. Okay, I'm going to do exact same thing and get the same answer, but slightly differently now. What I was going to do earlier, let's say this is t and this is t plus delta t, meaning this is still delta t right here, and this is still delta x, okay? And we're going to take a limit. So our velocity at 2 is still limit of delta x over delta t as delta t approaching 0. But instead of calling this point t, it's just 2 plus delta t. How's that? So what we will have is limit of delta t approaching 0 of the denominator is this thingy minus this thingy, which is just delta t now, isn't it? Well, this was delta t here. And then we have f of 2 plus delta t minus f of 2a. Wow, that looks mighty familiar now. Especially when I replace delta t with h, then that looks really, really, really familiar. It's something that has been drilled into your head since algebra 2 now, isn't it? Yeah, the difference quotient they call it. Ah, this is where it came from. Instantaneous slope of a curve. So everything that you've been trained to do up to this point is all leading into this point in time. Oh, that is spectacular now, isn't it? Okay, now, of course, h is so much easier. You're about to see why, but Newton did it this way. There are some textbooks who still use delta t. So I think you should see it at least once in your life. And then on the next example, I'm going to switch to h, okay? So let's do this with delta t, and you will see here why this is not preferable for many mathematicians. Okay, so this point is now f of 2, and this point here is f of 2 plus delta t, like that. So I have denominator still delta t, and then we have 2 plus delta t squared minus 2 squared, like that, eh? Okay, so as delta t approaching 0, we have 4 plus 4 delta t plus, here's the problem, that delta t squared. Do we need parentheses like that when we write the delta t squared, or is it delta t squared?
I was thinking we need a parentheses.
So delta t is delta times t, right? Okay, well, most books do put parentheses. Depends on who you talk to. Here's a little bit of history of math. Did you know that other than Sir Isaac Newton, there's another German mathematician who came up with exactly same thing? He didn't call it calculus, it was something in German, but his name is Leibniz. In fact, Newton kind of neglected to publish his thing, and Leibniz beat him to it, and then they later like accused each other of plagiarizing, and it was a big ugly history. Now, eventually Newton won, because he's technically the first one to came up with it, but about the same time, Leibniz came up with this, and then Newton took all of the credit. What's sad about that is, okay, fine, Newton beat him to it, fine, right? But we stole Leibniz notation. Most of the notation you will see in this calculus book everywhere is from Leibniz, and we gave him 0 credit. I know, this is like injustice. There is no justice in the world, since even back then. So And Leibniz called it delta t, one term. So we will not put parentheses, okay? It's pain in the butt to write it like that. Minus 4 over delta t. How about that? So far so good? And then of course, 4's cancel. And then we can factor and cancel delta t. So we have a limit, delta t approaching 0, and then 4 plus delta t. And then delta t approaches 0. So we have 4. Same answer as before, right? Okay, that's nice and swell. Any questions so far before I move on? Now, of course, well, let's find the slope of the curve at 3 now. At -5. I mean, we have to do this thing each time. That's a pain in the butt now, isn't it? So Newton thought maybe we should make a function out of this. Yeah, let's do that, huh? So here is a slope function, if you will. I'm gonna call it m at the moment, and I'm gonna change it. So have your erasers ready. M of t, slope function at any time, right? It is the limit of delta t approaching 0. There you only need one definition, and this is the original definition. Except now, instead of this point being 2, we'll just call it t, variable. And this is t plus delta t. So this thing is still delta t, and this thingy right here is delta x. So this point is f of t now instead of f of 2, and this point is f of t plus delta t. So far so good? But then remember this delta t was a pain in the butt? So we say same thing as h now, isn't it? So we switch it with h. H is equal to delta t, you get it? It's because of, it's just purely for the writing conveniences. So if we do such a thing, and let's write it, so instead of delta t, we let h approach 0, and then we have f of t plus h, this thingy right here, minus this thingy right here, so f of t over h. Wow, that looks really, really, really familiar. Now, we have literally done this 1,000 times, haven't we? Right, so this thing, now it's all downhill, evaluating t plus h squared minus t squared over h, and that is equal to h approaching 0 of t squared plus 2th plus h squared minus t squared over h, and then of course this thingy cancels that thingy, so we have, oh, color, I want black color back. This, okay, change the color now. Why wouldn't it, this computer is equal to limit of h approaching 0 and factor out 1h and cancel it, so it looks like this, and then h dies, so we have 2t, right? So if we, since this is a function, for any t value, it tells you what the slope is. So Newton called it, it's derived from f, so he notated with f prime of t, and he called this thing derivative of a t. I mean, this doesn't show up until chapter 3, but then you all know it, and I know that you know it, so it's like, what's the point of keeping it? However, something called the power rule, right, that all of you know, you're not allowed to use it until chapter 3. Like in the middle, when I release you from this burden, you will keep evaluating this limit. Any question? There are 3, 4 calculus teachers at Peninsula High, and all of us follow this protocol. You have to learn how to evaluate this limit before you learn something more convenient called the power rule. So if I see a power rule, it's automatic 0. Now, remember that velocity at 2? Well, that is, now we just put f prime of 2. And then if you plug in 2 here, of course that gives you 4. So it's convenient, but remember we wanted to do velocity at 3 as well? This is really, really convenient once you have it once. And besides, evaluating this limit with a variable t is easier than a number now, isn't it? Let's say -4, and say. So slope gives you, the derivative gives you a slope, which is same thing as velocity in physics, particle motion kind of sense. Questions? Okay, if there are no, suppose we want to draw the tangent at 0. I mean, you can draw the tangent here, no problem, right? Those are not a problem, but if you want to draw the tangent, if you zoom in really, really, really close, it still looks pointy. So if you draw it, is it, what did I do? Is this the right tangent here? Well, it looks good for this curve, but the other side, no, that doesn't look right. Then is this the right tangent here? Wow, that still doesn't look good. What about here? Well, that thing is rock. It's pointy. You cannot balance that thing up there. You know what I'm saying? So see, whole idea is, remember that talk yesterday, if you zoom in close to a curve, does it look flat to you? So the line, the curve and the tangent line look same. Here, if you zoom in very, very close, this thing will still look pointy, and that is our problem. Okay, so I'm going to calculate, wait, we're supposed to calculate the slope of this thing, right? Yeah, okay, so let's do it. The slope from the left-hand side, let's just do left limit first. Meaning f, can we just say f prime of 0 now? I mean, we all know what the slope means, so it's like we don't have to say slope, and yeah. This thing, of course, means limit as h approaching 0 are f of 0 plus h minus f of 0 over h, like that, right? However, there's a little caveat. H is slightly negative. You know what I'm saying so far with me?
Yes.
Okay, so it's slightly on, so it's like we are approaching it on this side. And I'm going to show you graphically what that looks like. So we go back here. So we have a point. Let's say, oh, it doesn't want me to, oh, yeah, there. And the other one is here. So if I let this thing approach, this is secant, but that's the picture. You get it? So we are trying to get that tangent. Okay. And then we expect this thing to be negative, if you can guesstimate it, right? Negative 2-ish is what that slope looks like, about. Okay, let's see how good our guesstimation is. So limit of h approaching 0, and then we substitute 2 minus 2, 0 plus h. Can I not write 0 plus h and just write h? Is that too confusing to everybody if I do this, or is it okay?
It's okay.
Yeah.
It's
Yeah,
fine.
good enough to do this, right? Minus, and h of 0 is 2, isn't it? I mean, f of 0 is 2, okay? If you plug in 0, you get 2, okay?
Yeah.
Over h. So far, so good? And then this thing cancels this thing, and we can cancel one of the h. So what we get is h approaching 0 from the left-hand side of negative 2 minus h. And h, of course, dies. So we get negative 2. Our guesstimation was pretty good, wasn't it? Okay. Now we'll evaluate the right limit. Okay, the right limit, of course, I'm going to show you here. So if we let this thing approach from the other side, then of course it's going to be pretty much a line, isn't it? Okay. So right limit, of course, you want it to be like that. So that's positive 2. That's easier to see. So right limit, so we have f prime of 0 is equal to limit of h approaching 0 from the right hand side of f of 0 plus h minus f of 0 over h, and h is slightly positive. Am I going to have enough room? Now we use the right hand piece, this one. So it's just 2h plus 2 minus 2, isn't it? Over h. I'm going to bring that down. Now, and then they cancel. So it just gives you 2. You get it? Now, derivative, remember derivative f prime of 0 is defined by, oh, I'm going to introduce you a new symbol that they use in college. Do you know what that means? It means by definition it is equal to. It's defined by, you get it? You don't have to use it, but it's convenient. Limit of h, this difference quotient, right? Now, in order for this to exist, the left limit and the right limit must agree. But in this case, we have -2 and +2. This is what happens in a pointy vertex. So we can say the limit does not exist, meaning the derivative at, so f prime of 0 does not exist. You get it? You see how that works? Now, this is a perfect segue to, well, where derivative fails to exist kind of thing. See, AP has put this kind of question before, and then, oh, because it's pointy, or actually there's a vocab, because it's cusp. Okay, whenever you say, the question is explain, justify, why, how, one word answer is usually not the right answer. You don't want to say it like that. This is the model answer, but at minimum, you must say the left derivative and right derivative are not the same. You get it? Slope on the left is negative, slope on the right is positive, so they're not the same. Because the definition of derivative is this limit. How about that? Okay, well then we'll do this one, and we are just finding a derivative at point at 1 with the alternative definition, correct? So let's do it. So we'll say s prime of 1 is same as limit of, this time t approaching 1 alternative, right? And then we have here t minus 1, and then s of t minus s of 1 is how you evaluate alternative derivative. Okay, and your s function is 1.86 t squared minus 1.86 times 1/8. You don't have to show me times 1. So for so good, let's factor 1.86 because that's one of the property of limit. You can do that. It's a constant. And then we have t squared minus 1 over t minus 1. Oh, that factors. And then cancels to be this, right? And that's 2. So this is a difficult part. What is 2 times 1.86? Oh, 3.72, right? I think I got it right, meters per second. How about that? Good? Okay. 29, horizontal tangent. Oh yeah, this, if the parabola looks like this, it has to be flat right here. You know what I'm saying? So what it's saying is slope. meaning the derivative is equal to 0. So first thing is we have to find what this is. And that is the limit of, oh, by the way, this literally have this requirement to write the difference quotient?
Yes.
Okay. Here's the good news. Now you have, I mean, it's a very good requirement. So to drill it into you what derivative means. But here, now I hereby release you from this burden. You can start with the second line. I'll still write it, but you don't have to. If I see this line written correctly, then I'm gonna assume you know what the hell you're doing. How about that? And if you screw this up, it's not like I'm gonna give you partial credit for stating the formula or definition. You know what I'm saying? There's no partial credit for that. So it's useless to me now. Okay, now this is of course
Negative.
Huh?
Can we distribute the negative?
Yeah, sure.
Oh, thank you.
But don't screw up. Whenever you try to cut corners, that's fine, as long as you don't screw up. The reason I like doing it this way is everything that was on the right inside here must cancel. You get it? So then I cancel it from the right hand side like that. And if there's anything left over, that means you screwed up. Okay, so it's a nice reminder. Now, so then you do have to write this and open parenthesis and cancel one of the h and plus 1, right? Did I miss something?
I think it's plus.
I think it's.
I'm afraid I missed something, right? Oh yeah, I missed that 4.
Oh.
I missed the 4 right here. Okay. Okay, good. So for a second, we're back. And of course, h dies. And this is my notation. You don't have to write it. Right, this is the slope. Now, my step is, we'll say this is equal to 0, be professional about it. This slope needs to be 0 for what x, you know what I'm saying? And that, of course, you don't have to show me this work, x is equal to -2. You know what I'm saying? So this thingy, if you put -2, and then your y value is -5, right? So that becomes your answer. That's where this is flat. You get it? Or better yet, how about that? Any questions?